All right, welcome back, everyone. So I hope that you have figured out what the limit is, at least. So everyone in the room, you decided the limit was what?
12.
12, that's right. So you could either plug in values of x very near 3, or graph this, or in some way find the limit. So if you found a different limit at home, you could pause the recording right now and go back and try to get 12. And then we'll start the scratch work. So the scratch work starts off the same. Given epsilon greater than 0, we have to find the delta such that this. What are we going to put in here now for our limit? We just decided it was 12, right? So now saying f of x minus 12 is less than epsilon. We just replace f of x by its formula, and minus 12. And then just like we did in example 2, we factored a 2 out of the numerator. Here, we can factor a 6 out of all those terms, right?
Yes.
And when you factor out a 6, you'll get x squared minus 4x plus 3, which conveniently factors as well, just like it did in the previous example. L is still 12 here. And now we would like to cancel the what's here.
X minus 3.
And we're allowed to cancel that. We know we're not canceling 0 over 0 because we know x does not equal what?
Oh.
We know x does not equal
3.
3, right? Because we're taking the limit as x gets near 3, meaning we don't care what happens at 3, only near 3. And in the proof, we're going to start with this statement 0 less than x minus 3. And the exact purpose of this 0 is to prevent x from being exactly 3. So that's why we're legally allowed to cancel those. So then the 12 is still there. And now if we simplify this, we get what? 6x minus 6 minus 12. So altogether 6x minus 18. And look at that. You can factor a 6 out of that. And there's the x minus 3, just like we were hoping to get. Because x minus 3 is the quantity we have control over. We control how far in the x direction we move from 3. So then if we divide the 6 to the other side, we get epsilon over 6. So that's what our delta should be for this one. So that if you did the scratch work at home, you should also have ended up with delta being epsilon over 6. Any questions on the scratch work?
Professor,
Yep.
the previous one, when I just came in, when I asked you about the canceling thing, and you said you didn't cancel it, but here you say you cancel it.
Right. So the question that you asked before was in the proof part. And in the proof, we're doing the scratch work backwards. So here, we did cancel the x minus 3s in the scratch work. Now when we do the proof, we're going to start with this line and work backwards. And so instead of canceling the x minus 3s, we're going to multiply by x minus 3. Right. So the proof ends up being the scratch work done exactly in the opposite direction. Does that make sense? OK. All right, so let's do the proof. So again, all these proofs start the same way. Suppose epsilon greater than 0 is given by this person on the street. It's our job to find the delta, such that if 0 less than x minus 3 is less than delta, then f of x minus our limit, which we decided was 12, is less than epsilon. We choose delta to be what? Epsilon divided by 6, because we've done the scratch work. The person who's reading the proof is very impressed with us, because how on earth did we know that? So we start with, we're trying to prove a statement, again, of the form if P, then Q. So we start by assuming the P part. 0 less than x minus 3 less than delta. Delta is just epsilon over 6 for us. And we're going to keep this 0 as long as we need it. This 0 is preventing x from equaling what number? 3. So as long as, until we use this point here, where we multiply by x minus 3 over x minus 3, we need to keep that 0 along with us. So now we're going to go backwards from the scratch work. So this was our last line in the scratch work. The next thing is to move the 6 to the, multiply everything by 6. When I multiply 0 by 6, I just get 6. I just get 0, right? So nothing changes with the 0. If you find yourself at home sometimes writing epsilons as 3s, that's a common thing to do. Don't feel bad about that. It's easy to get them mixed up. So then the scratch work says the next thing to do, I guess we sort of skipped a line in the scratch work here. Maybe we'll do a separate line in the proof, is to move the 6 inside and write it as 6x minus 18, right? So maybe when you were doing the scratch work at home, you wrote that step out. I guess I skipped it here. And then we want to take that nice, simple-looking 6x minus 18 and rewrite it in this more complicated way And the reason we know how to do that, and the reason that we know that we ought to do that, is simply because we have done the scratch work. And we're still keeping the 0 there because we haven't multiplied by our x minus 3 over x minus 3 yet. But that's what we're going to do now. Now we will multiply by x minus 3 over x minus 3. And then, so to answer your question, the reason that that's legal now is because this 0 all along is keeping x from equaling 3, right? Here, if x is 3, we're not greater than 0, so that's not possible. If you plugged in x equals 3 here, you'd get 0 in here. 0 is not greater than 0, so x can't equal 3 there as well, or there, or there. But now that thing on the inside is almost exactly what we want. And we don't need the 0 anymore, so we can drop it and draw a one-headed arrow. If you distribute out this numerator, because that's what we got by factoring that, we just get 6x minus 24x, 6x squared minus 24x plus 18 over x minus 3 minus 12. And that's exactly what we were aiming for, right? We wanted to end up with f of x minus 12 less than epsilon, which is exactly where we've landed. So as desired. So the mechanics of this proof and this scratch work are very similar to what it was in problem 2, just a different function, maybe slightly more complicated algebra, because the factoring was a little bit more complicated here. But this really proves that the limit is 12. So first you had to figure out what the limit was. However you did that, you decided somehow that it was 12. You did your scratch work to figure out what the right delta to choose was. And then you just did the scratch work backwards. All of the effort, all of the thinking goes into this part in the scratch work. It's when you're working backwards in the proof, you almost don't need to think at all because you've already done all the trouble in the scratch work. What do you think about these proofs? So as I was saying, these were all chosen. These are all essentially, the first one was a perfect linear function. Examples 2 and 3 are also linear functions just with a hole in them because they're undefined at x equals 3 here and at x equals 1 in example 2. But if you graph them, they're also perfectly straight lines with holes in them. And that's why the scratch work works out perfectly, and we're able to hit the corners, as we said last week in that app. The example that we're going to do next week, first of all, is one where that doesn't work out so nicely. So we'll need to be a little bit more creative in the algebra that we're going to do in the scratch work and then in the proof. And we will also do another proof next week, this proof technique called proof by contradiction, because if some of your lessons that you guys are going to do will involve proving that a limit fails to exist. And the way that you do that is by this technique called proof by contradiction, where you assume the limit does exist, and then you show that that leads to something that is impossible. So that's what we're going to do next week. We'll be glad to see you then.